Time we had talked about section 1. I think I'd asked you guys to, well, we could have done up to 16 from the problem set. Start with some questions, if there are any, from the problems. So at this point, you guys could have done up through 16. Okay. We can always circle back if you run into something later on that you want to talk about, so no big deal. Guess we'll just get started then. So 15.2, we're going to be talking about exponential and logistic modeling. So this is just kind of an immediate extension of things that we were working on in section 1. So should be relatively straightforward. Which is nice. So we're mostly going to be just kind of looking at some specific models and formulas and kind of solving some story problems involving those things. So it's nothing crazy. So the first situation we're going to look at is the exponential population model. So the exponential population model, we have P of t equals P naught times the quantity 1 plus R over 100, all to the t. So our P of t is a population at time t. P naught would be our initial population. What does initial mean again? Yeah, like the first or starting, or R is going to be the rate of change. And we should express this as a percentage. And then t is going to just be some measure of time. And the unit of time that we'll be using should kind of match the unit in the rate of change. So if it's 5% per year, then we'd probably want to describe the time in years. If it's 5% per month, then we'd want to describe the time in months. If it's something weird, like 5% every 37 days, probably describe it in terms of days, but we'll have to modify our t a little bit to deal with stuff like that. Okay with that idea? All right. So I want to point out to you, when we talked about exponential functions last time, we said that we could write them in this form, a times b to the x. So in that sense, p naught is like our a, and then 1 plus R over 100 is like our B. So keeping that in mind, we can talk about whether a population model is growth or decay. So let's look at a specific example. And I'm going to be mostly just kind of copying and pasting from the lessons because, well, there's a lot of words in here and it's just going to be a little bit easier for me. So this question is going to ask us to do two things. First, to determine whether these are growth or decay. And then second will be to find that that rate of change, whether it's a rate of growth or decay. Everybody cool with the questions asking? So in the first equation here, so really probably should say okay, fine. Just be stuck. There we go. In equation A, what do I need to, what number should I be looking at to determine whether it's growth or decay? So both of those answers were incorrect. That's okay though, I appreciate the participation. So which number am I needing to be looking at? The value for B, which in this case is 1.0384. So remind me again, what is the criteria for telling if this is growth or decay? This was something we talked about in the previous section. Super important to remember.
B is greater than 1.
Very good. So as long as the leading or that initial term is positive, if the long as the B value is greater than 1, that's going to tell us it's growth. So if I look at equation B, so if it's greater than 1, it's growth. What do I have to be decay? Less than 1. But remember, those values of B also have to be positive. So we can see that the first one is growth and the second one's decay. Everybody's cool with that? What happens if the A value is negative? Just the rule flips, right? So if A was negative and B was greater than 1, it would be decay. And if A was negative and B is between 0 and 1, it would be growth. That's all. Okay, so we sorted the growth and decay part out. How are we going to get that constant rate of change part? Well, remember what I highlighted in green here earlier? That 1 plus R over 100 is really the same thing as our B. That's what I'm going to use. So for the first one, I'll just say this. And now I can just solve for r. So we'll subtract 1 from both sides first. And then multiply both sides by 100. There's my value for r, and remember r is a percentage. So I have 3.84%. Cool! No big deal. So if I do the same thing here for part B, so subtract 1 from both sides, and then multiply both sides by 100. And the r there is negative 1.33%. What do you notice about the r for the decay? It's negative. And what do you notice about the r for the growth? It's positive. Oh, shocking. Shocking result. It's not that shocking. I was being sarcastical. Nobody thinks that's funny today, huh? Well, that's fine. You don't have to laugh at me attempting to inject some humor and make class interesting. I'll just be as dull as I possibly can from now on. If you thought I was being dull before, just you wait. The next question, I'm asking you to determine the population model with an initial value of 15, increasing at a constant rate of 6% every year. It should be clear from the context of the question that we should be using the population model described earlier in the lesson. So we begin with P of T equal P naught times the quantity 1 plus R over 100 to the T. Next, we should begin by filling in values for P naught and R. What should be the value of P naught? 15 is correct. What should be the value for R? 6 is correct. And if we choose to simplify, we would write 15 times 1.5 0.06 to the t. All right, who's convinced I can be even more boring than I had been being?
I think you can.
You think you can? Yeah. Yeah, it's basically try to just sound like text to words. And it was terrible, right?
Yeah.
Yeah. Okay, let's not do that again. All right. So there, we wrote our model. Big deal, right? Okay. Let's see another example then. Again, I'm just gonna copying and pasting these examples from the lessons so that I don't have to spend a whole lot of time writing them down. So this one says, determine the population model with an initial value of 15, increasing at a constant rate of 6% every 6 months. Oh boy, Mr. Gulick, this sounds almost exactly the same as the other one. There is one important difference. What is the difference between this question and the previous one?
You have to put 6 on,
The what?
but it's every 6 months. And you put 6 on.
Well, I'm not sure we want to do that.
26.
Well, it depends. It depends a little bit. So right here in the first one, we've written our model with t in years, right? It'll depend a little bit on what unit we want to use for t on how we write the second one. So just like before, our initial value is 15. Our R is 6. But we have to deal with this now every 6 months part of the rate of change, right? Now that is going to affect what we write in the place of t. But first we should decide which unit we want t in. So do we want t in years, or do we want to write it in months, or do we want to write it in some other way? Well, let's write it in years first. It doesn't really matter which one you choose, but the answer will be different depending on the unit for t that we choose. So let's say we write this in year. T will be in years. Reasonable. What does the rate of change happening every 6 months mean now for t?
1 half a year.
Okay, so how many times does that rate of change occur in 1 year? Twice. So instead of writing t, I'm going to write 2t. There you go. Very good. Okay. Or maybe we decided to write this in months, right? Not unreasonable to do that. That would be the other obvious choice. Well, how many times does that rate of change occur in 1 month? 1/6. Very good, because there's 6 months for a rate of change. So inside of 1 month, we've done 1/6 of that. So we'd write this as t over 6. So in this question, where they're not specifying what unit of t to use, either of these answers would be correct. Okay? Either of these answers would be correct, but in the problem like this, you definitely want to make sure you're stating how you're measuring t. Does that feel okay to you guys? Yeah? All right, let's do another. Suppose that a colony of 120 bacteria is put into a petri dish and the culture doubles every 3 hours. Predict how long it would take for there to be 400,000 bacteria. So this question's a little bit more involved, right? We're going to have to do two things here. First, what do we need to do? We need to make the equation. So we're going to need our model. Is this clearly a population model? Yeah, right. We're talking about like some number of organisms and that, them reproducing or whatever, right? So it seems like standard, super obvious population situation. Not that we have another model right now, but we will eventually as we work through these sections. We'll be adding to our list of different exponential or logistic models. And I know you guys are just like super thrilled to hear that. But it'll be okay. All right. So let's start filling this in. We need to fill in values for P of T, P naught. Blah, blah, blah. What is our value for P naught? 120. That's the initial amount. Everybody cool with that? Okay. A little bit trickier. What is going to be our value for R? It doesn't give us a percentage explicitly, right? But there's a word in here that's telling us what we need or how the change is occurring. What word do you guys see in here?
Doubles.
Doubles. So this is somehow going to be giving us our R. What does doubling mean in terms of a percentage? Well, not 200%. So if you had 2 things, and then you would have 4 things,
100%.
it's a 100% increase. Very good. Does everybody see that as, if you actually think about what's happening, that doubling is the same thing as a 100% increase since you're getting 100% of what you had before added to it? Okay, so here's our model then, but we still need to do one other thing with our model. What else do we still need to worry about? The time, yeah. So how often is this doubling occurring? Every 3 hours. So it probably makes most sense to think of T in hours, right? So what would we write there in the exponent? If T is happening 1 hour, how much of a rate of change do we get in 1 hour? 1/3. So I'll write that as T over 3. I guess color code the rest of this stuff. And if I want, I could simplify this down. 100 over 100 is just 1, and 1 plus 1 is 2. And now that I've simplified that, boy, that looks a lot more like doubling, right? Or just multiplying by 2, some power of 2. Okay, so there's our model. That's step one. What are we going to be doing in step two? We're going to be solving that model for some value, right? In that last sentence, it says, predict how long it would take for there to be 400,000 bacteria. What are they asking us to solve for? T or P of T? Because those are the two variables we have, right? The question says, how long? So we're solving for T, which is just time, right?
Oh, yeah.
P of T is the population at a certain time. So we're solving for T. So we have to plug some value into P of T. So we need to plug a population in the future into P of T. What are we going to be doing? What population are we going to be using there? The 400,000. So the equation we're solving is 400,000, ooh, Boise, equals 120 times 2 to the T over 3. Yes, sir. Of course. Now, to solve this, since we have a variable in the exponent, algebraically, what would we have to use to solve this? If you have a variable in the exponent, it starts with an L. A logarithm, that is correct. Have we talked about logs yet this year? No. Do you suppose I want you to use a logarithm right now to solve this? No. What are we going to use to solve it? A graph. Yeah, we're just going to solve this with our calculator by graphing. So the easiest way to do this is to take the left-hand side and put that into y1 or y2. It doesn't really matter. And then take the right-hand side and put it in the other space. Everybody feel good there? Now, we do have to be a little bit careful about setting our window. So let's think about what's happening here. After 3 hours, we'd have 240. After 6 hours, we'd have 480. After 9 hours, we'd have 960. So it's going to take a while for that to get to 400,000, right? So maybe I'll go 0 to 100. I'm just taking a stab at it. I don't really know, but I'd rather overestimate than underestimate. Cool with that. Our y's are going to be the population size. What's the smallest population that we have? 120, right? The initial amount. I'm just going to use 0 as the minimum there because 120 is still pretty close to 0 when your maximum value we care about is 400,000. I'm going to pick something a little bit bigger than 400,000. I'm going to do 500,000 just so I can make sure that I can see the intersection nicely. And then, I don't know, let's go up by 50,000s or something. Is that? Yeah, that's the right number of zeros. And let's hit graph and take a look. So there's my 400,000 line. Here's my population model. Whoa! I got there pretty quick. Doubling is steep, guys. Boy, that gets darn near vertical pretty quick, right? Exponential growth is fast. Okay. So to find the intersection there, I'm going to do second and trace. Select the intersect command. Because we only have 2 curves that we've graphed, and there's only going to be one intersection, it doesn't matter the answers to the questions that I give, so I'm just going to press enter 3 times real quick. And the calculator spits out about 35.1, and since t is in hours, That would be hours. Does that feel okay to you guys? Yes. Good. Very similar to the techniques we used last section, right? No new technique really going on here. We just introduced this new model and you're writing your own model. No biggie. Another place where we can use this population model is a specific situation called radioactive decay. If you've taken a chemistry course, I believe this should be something you talk about and perhaps even solve radioactive decay problems. But I don't know. I don't know exactly what you guys do in your chemistry classes, but I suspect this is something that you would do even in a first-year chemistry course. What does radioactive decay mean? It's the process in which a number of atoms for a radioactive substance change from a radioactive state to a non-radioactive state. Each element in the periodic table does this at a fixed amount, or for a fixed amount per unit of time. The half-life of a radioactive substance is the time it takes for exactly half of that radioactive substance to become non-radioactive. In terms of us, half-life is going to be giving us our value for R. So whenever you hear the half-life, the R is fixed. What will the R always be? Close. Since it's negative, or since it's decay, we know the R value has to be negative, right? Everybody's agree with that? We mentioned that earlier. And if we're talking about cutting in half, the R value should be, remember it's a percentage, 50%. Yes, very good. So whenever you're dealing with a half-life problem, we know the R is negative 50%. Okay, let's do an example now. Not much different than what we've been doing, right? It's a different context. It's a little bit less clear that like this can still be a population problem, but it can still just be a population problem. So again, we'll still just be using our population model. Worth pointing out, though, we're going to be doing the same strategy as before, right? This is going to be a two-step problem. We say, suppose that the half-life of a certain radioactive substance is 35 days, and you have 10 grams of the substance initially. Find the time it would take for there to be only 1 gram remaining. So again, 2 steps, just like the previous problem. First step, we're going to have to write our model. And then second step, we're going to have to solve the model for some specific value that it's given us. Okay. So the first thing, let's get this model written. We need an initial value. We need a rate of change. And we need to adjust our time variable if necessary. What is the initial value here? 10, because it says 10 grams of the substance initially. Very good. What is the R value? since it's talking about half-lives, the R is always negative 50%. And then to decide what our exponent should be, we need to decide on what unit of measurement we need to be talking about our T in. So in this problem, since the half-life is described in days, it probably makes more sense to have T in days. Everybody's cool with that? So how many half-lives occur in one day? 1/35. Very good. So I would just make that T over 35. Everybody happy with what we did there? Okay. Now comes, we've written our model, so that's good. Next, we want to solve it for some specific value. So the last sentence says, find the time it would take. So which are we solving for, T or P of T? Find the time it would take. T. Very good. For there to be only 1 gram remaining. So that 1 gram is our P of T, right? That's the future amount of radioactive substance we have. Notice that 1 plus negative 50 over 100 is just going to be 1/2. And now this should look a little bit more like a half-life problem, right? With that 1/2 sitting there. So now it's just calculator time. We'll do the kind of the same thing we did before. So into Y1, I'm going to put 1. That's my future value. Into Y2, I'm going to have 10 times 0.5 to the X over 35. And now let's set a window here. So the X's are times. So after 35 days, I'd have like 5 grams. After 70 days, I'd have 2.5. After 105 days, I'd have like 1 1/4. So it's going to be at least 105 days. Let's just make it 200. We'll probably see it by then. Everybody feel cool with that reasoning? Again, I just want to try to get a feel for how big that upper bound needs to be, and then I'll make it way bigger than I need, because I definitely, there's no harm in making it too big. If you can't see the intersection because you made it too small, oops daisy. You just have to go back and make it bigger, but I don't want to have to go back. I'm just going to make it way bigger than I need. All right. The Y minimum, what's the smallest amount of substance we can have in radioactive decay? 0, right? Till you can just decay until there's nothing left. Feel good there? What's the maximum amount we can have in this problem? 10, the amount we started with, right? Because it's decay, so it's just going to be getting less, right? Everybody cool? So I'm just going to start that with 10. And then we'll go up by 1s, and that feels good. Let's hit our graph. There's my line for 1 gram. There's my decay curve. There's my intersection. Second, trace. Pick the intersect command. And then enter 3 times. And I get 116.3-ish days. Everybody cool with what we did there? Okay. Now, remember that when we talked last time, we talked about exponential and logistic functions. And we talked that oftentimes the logistic functions give us a more reasonable model, especially for things like population, because, well, there's often limits to the size your population can get. Like there's only so much space to put your items, or there's only so many resources they can consume. So there's often like an upper bound to like how big a population can grow. So a logistic function is often a better model for these sorts of things. So let's look at another population problem. This one is using a logistic function, but in those cases where we are asking you to use a logistic function, we'll just give you the logistic function. We won't ask you to create your own. Is that okay? All right, you start a bunny petting zoo. Aww. You determine that the population of bunnies on your farm can be modeled by the equation B of t equals 800 divided by 1 plus 99 times e to the negative 1.5 t, where t is measured in years. How many bunnies do you have initially? What, Mr. Kulik? 800 is incorrect. What time is represented by initially? What value of t would you say is initially? What does initially mean again? The first. So what would be the value of t here? Negative what? Zero, right? If nothing has happened, that would be no time has elapsed. That means time 0, right? Initial is the start. That means no time has elapsed. That means time is 0. Everybody feel okay with that idea? Important, like little, just a logic problem there or whatever. English grammar problem? Is that a grammar problem? I don't know. So what am I going to do? I'm going to take my b of t function and plug 0 in for t. Okay. Let's use a different color. Negative 0.5 times 0 is? Okay. E to the 0 is 1. 99 times 1 is? 1 plus 99 is? So we would have 8 bunnies. 800 was a little bit of an overestimate there. Is everybody cool with how I did that? Very easy, right? The hardest part was figuring out what initially meant. Part B. What is the maximum sustainable population of bunnies on your farm? So remember here, logistic functions have like an upper and lower bound, right? So this upper bound is the one that we're looking for. Does anybody remember how to find that upper bound for a logistic function of the form? We talked about this last time. Anybody remember? The upper bound is just y equals c. And the lower bound was, does anybody remember that one? Zero. Again, if you think about it like it's measuring a population, what's the minimum population you could ever have? Zero, right? You can't have negative things, right? Okay. So, let's go back to ours. Function we're using here. We know we're looking for C, y equals c. We're that c. So what is the c in our equation? Landon. You said the answer already. 800, yes. He tried to answer part A as 800. Everybody cool with what we did there to get that one? Again, did we have to do anything? No, we just had to remember some stuff, right? It was almost more like a science question than a math question, you know? Last one, it says, how long will it take for you to have 500 bunnies? What are we solving for here when it says how long? T! So I'm just going to plug 500 in for B of t. And I'm going to need to solve this. How am I going to solve that? Where's the exponent located? Or, I'm sorry, where's the variable located? In the exponent. So to solve this, what would we have to do algebraically? A logarithm. Have we talked about how to use logarithms in this class yet? No. So how are we going to do this instead? Graph it. Those of you that are taking ACTs in the future, this is a super effective solving technique. In particular, if you run into a problem, you're like, I don't know how to solve this thing. Just graph both sides of it and find the intersection. There might be more than one intersection, but that's okay. If you don't know how to solve it, you can still use this method. Remember, how did I get the E button? Second, and then LN. The LN is there on the left-hand side, a little bit up from the on button. We'll set our time here. I don't know how long. 0 to 200 seems reasonable, though. Actually, no. Wait a minute. 200 is a super overestimate. I don't know. Let's just do 50. I'm just guessing. And I know this. So 0 to 800. Since I know 800 is the max, right? That's no biggie. Let's hit it. There's my line at 500 bunnies. Whoop! There's my logistic curve. Those bunnies are growing fast. It's almost like they're reproducing like rabbits. Wait a minute. They are rabbits. So we're looking for the intersection. I use second trace, then select the intersect command, enter 3 times. And I get about 10.2 for t. What unit of time was t being measured in? It was years. Hope you had a lot of rabbit hutches built for your petting zoo, because you start off with 8 rabbits and 10 years later you have 500 is kind of a problem. If you weren't planning for that, you know what I mean? I'm just saying. All right. So to this point, you guys should be able to do up to 36 now. We're going to stop here for today because I don't want to get into the next section yet because Well, it's kind of a big, deeper section. I don't want to go like halfway through it. I'd rather do it all in one shot. So this feels like a good place to stop. You guys should get started on your homework. If you haven't done up through 16 yet, you should probably get on that. If you've already done that, you can start here on this 17 to 36. Cool beans? While you guys are working on that, I want to say a couple of words here.